Alright, good morning everybody. Class recording for today has started. So, up on the board, you have three pictures of three substances, and they're not labeled, but they are three different states of matter. And way back in, I don't know, second grade or something, you started learning about different states of matter. And up on the board, we have three states of matter: gas, liquid, and solid. Those are the three that you guys learn about the most, but there are a couple other states of matter that exist at extreme conditions. Not so much here on Earth, but there's some other ones out there, just so you know. I won't make you learn them right now, but we're going to talk about these three. So, when we learned about these three states of matter, you learned a couple of properties of solids and liquids and gases. For example, what did you learn about solids back when you were learning about states of matter? If somebody said to describe a solid, what would you say to them? They hardly move. That's not the first thing you learned, Eric. So you learned that a little bit later on. So what makes something a solid? There are two properties that everybody learns about the first time you learn about solids. Doesn't fill its container, so it has a defined what? Shape and a defined size or volume, right? Okay. So when we talk about solids, solids have a definite shape, right, and a definite volume, right? They don't fill up the container that they're in because the container that they're in doesn't matter. This baseball will be round and this size, whether we put it in this room or whether we put it in the gym or whether we take it outside to the football stadium. It's a solid. It has a definite shape. It has a definite volume that doesn't change, right? Okay. Along those same lines of thinking, what about liquids? Definite volume, but no definite shape. So we'll go like this. And then we'll use fancy colors to do that, right? Wow, that is okay. So, what does that mean? Something has a definite volume, but without a definite shape. You describe it to me.
So it has the same amount, but
what does the shape of a liquid depend on? The container that it's in, right? It's the same amount of stuff, right? It takes up the same amount of space, but depending on the container that it's in, right, that determines what shape it is. Okay? And then finally, gases, right? What do we know about gases? Say again? Okay. So, gases have no definite shape and no definite volume. Meaning they'll do what? Go anywhere and everywhere that they're allowed to, right? They will completely fill up the container that they are in. Yes? Right? And you can experience that back, I don't know if it happens too much here. I don't have lockers in my hallway. And I don't think this happens as much anymore, especially not in high school. Maybe this is more of a middle school thing, but there was a time in high school where body spray was really like in, you know? And so somebody would spray body spray somewhere by their locker, but not just like a little bit, like half the bottle, you know? And then it would just seep into the entire hallway, yes, right, okay? Because gases take up their container, right? If you let them spread out, they will spread out as much as they can, okay? So, we learned about those, and those like you learned about that, like you were, like I said, you were in second grade, and you started learning about solids, liquids, and gases, right? So, Eric, you wanted to take our discussion in a different direction, right? What direction did you want to take our discussion? Good, the movement of the particles, right? What were you saying about the movement of the particles of a solid? They hardly move, right? So here, the particles, we'll go blue on this one, okay? So, particle motion is pretty low. Are the particles of a solid still? No. They do move, but they're sort of fixed in place, right? They kind of like vibrate, and jiggle, and twist and turn, but they don't actually go anywhere, right? And then liquid's kind of hard to, you know, it's sort of the middle, because that's what it is. And then what about the particle motion of gases? Really bad, really high, right? So here, this has big particle motion. All right. There's one more thing that contributes to these definite shapes, definite volumes, no definite shape, no definite volume. There's a motion component, which we've already discussed, but there's also an attraction component, right? Solids don't, or the particles that make up a solid don't move very much. Why not? Say again? They're attracted to each other. So these particles that make up a solid, they don't move very much, and the reason that they don't move very much is because there's a lot of particle attraction. And then on the other end of the spectrum, what about the attraction between particles that make up a gas? There's hardly any attraction between particles that make up a gas. So the reason I start with this is because the first thing we wrote down was a set of properties, right? Definite shape, definite volume, no definite shape, no definite volume. But when you start examining the stuff that makes up those substances, we see there is a reason behind why solids have the properties that they do, why gases have the properties that they do. And we're going to focus a lot on that today. How compounds are based on the bonds that hold them together end up with a certain set of properties, right? So with that being said, let's go here, and let's go here. All right, properties of ionic and covalent compounds, when we get into intermolecular forces. We're not actually going to start with intermolecular forces, but that's okay. So, physical properties and bond types. The physical properties of substances are affected by the attractive forces between the particles. The attractive forces then also affect how much movement those particles have. So it's kind of a trickle-down effect, right? The attractive forces affect the movement then affects the properties that we observe about those different states of matter. And the greater attraction there is between the molecules, the more energy is required to overcome those attractive forces, right? Remember, it all comes back to energy, yes? Right? Energy, the ability to do stuff. So if you have a greater attraction, or the greater the attraction between the particles that make up a substance, the harder it is to separate them. And that leads them to move less, which tends them towards a certain set of properties. Molecules that have greater attraction generally have increased melting and boiling points because we're taking those particles from less movement to more movement, right? When we melt something, we're turning it from what to what? Solid to liquid, so the amount of movement has to increase, right? When we take something, or when we boil something, we're taking it from what? Liquid to gas, right? So now those particles have to move even more, right? The more attraction there is between those particles, the harder it is to do these things, right? And that means we have to heat them up to a higher temperature because that relates to more energy, etc., etc., etc. Okay? Good there? All right. So let's first talk about ionic solids. Okay, there's a reason why we talk about ionic solids. So ionic solids are going to be held together by what type of bonds? Ionic bonds, right? And as you can see in this picture over here on the side, and I think you guys have a copy of it on your outline as well, right? Yeah. It's not in color, but right. So the smaller spheres in this representation are pointed out as sodium, right? And then the bigger green spheres are labeled as chlorine, right? So this is sodium chloride. We talked about that when sodium bonds with chlorine, right? Sodium has how many valence electrons? 1. Chlorine has 7. So what kind of ratio do we need to make everybody get to their 8 valence electrons? I suppose 4 to 4 is a correct answer, right? When we did it in class, we did it as a 1-to-1 ratio, right? 1 sodium, 1 chlorine, everybody's happy. But here, you can see that there isn't just 1 sodium and there isn't just 1 chlorine. It's an alternating pattern of chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium. If we were to look at the ratio of sodiums to chlorines within this block, right? Depending, it might not work out that way because of what they're showing you and stuff like that, but, right, there would be a 1-to-1 ratio within this block, right? It's not necessarily just 1 sodium and 1 chlorine, but when we get a group of them together, we do have that 1-to-1 ratio. This 3-dimensional structure is something that we call a crystal. Ionic compounds will form these 3-dimensional structures that we call crystals or crystal lattices. Those two terms are synonymous. We can use them interchangeably. And what ends up happening is that each ion, whether it's the positive sodium or the negative chlorine, is attracted not just to one of those other ions, it's actually attracted to many of those other charged ions. And so, we end up with something that looks like this. So here is a crystal, or a representation of a crystal, that represents sodium chloride. All right? It doesn't exactly say which ones are which, but let's say the reds are sodium and the whites are chlorine. Okay? So we have this sodium right here, and we can see that right next to it is a chlorine. But there's also a chlorine on the other side of it. Right? There's also a chlorine above it here. And there's one down here. And if we tilt it, there's one right here as well. Okay? What holds the sodium ions and the chlorine ions together? The fact that one's what and one's what? One's negative and one's positive. When this sodium loses its electron to chlorine, let's say it was this chlorine that it lost the electron to, this sodium becomes positive, this chlorine becomes negative, they're attracted to each other. However, this sodium is still positive, even though it's attracted to this negative chlorine. It doesn't cancel out the fact that it's positive, right? If you have two poles of a magnet, a north pole is attracted to a south pole. That doesn't make the north pole not a north pole anymore, right? So, this sodium may have lost an electron to this chlorine, but this sodium lost an electron to this chlorine. So these two are attracted to each other. But even though this one is still positive and attracted to this negative, if this negative came around, it would still be attracted to it. So just because this positive chlorine or sodium is attracted to this negative chlorine doesn't mean it's not attracted to every other negative chlorine. It is. And so what ends up happening here is that these two atoms don't just stick together. They start finding the other positives and negatives, and we end up with this three-dimensional network of alternating positives, negatives, negatives, positives, negatives, negatives, positives, negatives, positives, right? Each red is surrounded, and let me see if I can find another red here. Oh. Yeah, we can go like, just like corner here, right? Each red is surrounded on all sides by white. And each white is surrounded on all sides by red. And we get this three-dimensional network that we call a crystal. All right? Does that make sense? Okay. Sometimes we can get crystals that don't have an even number of positives and negatives, right? Depending on the number of valence electrons we trade or lose, we end up with a more than 1-to-1 ratio sometimes, right? And so here, this red is not just, all right, there's not an even number of reds and whites in here because the reds, let's say, have a +2 charge, whereas each white only has a -1 charge, right? Then we'd end up with a 2-to-1 ratio in here. But still look, all nice and alternating, right? White, 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 red, white, 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 red. We still have that pattern of positive, negative, but it might not be an even 1-to-1 ratio. Okay? Does that make sense? So, what does that do to properties? All right. The crystal is formed because of the attraction of oppositely charged ions. But there is a greater attraction between ions of greater charge. These are the strongest kind of forces that we can see when we talk about attraction between particles. Interionic forces. Interionic forces are going to only happen after what? What has to occur first before we get interionic forces? Well, finish writing. Go ahead. Interionic forces are basically an ionic bond, just instead of having two atoms held together, we have multiple atoms held together. But what has to happen first, even before an ionic bond forms, or before interionic forces form? We have to make what? Interionic forces are between what? Ions, right? What are ions? Atoms that have done what? Lost or gained an electron, right? Before this happens, we need to have transfer of electrons between metals and nonmetals, okay? Once that happens and we have positively charged metal cations and negatively charged nonmetal anions, now they are very strongly attracted to one another. So, what we see in ionic compounds, we see compounds that have very high melting and boiling points. Most ionic compounds are solids at room temperature because there is a lot of attraction between these particles. That means it's hard to separate them, to make them move faster like they have to turn it into a liquid or down the road into a gas. Okay? A lot of them dissolve in water because water can get into these spaces and break it up. Right? Yeah, so water can get into those spaces and break up these red and white spheres. Okay? They can also actually conduct electricity if they're separated. Right? Remember that electricity is a flow of charge, right? Charge doesn't flow so good here, right? But if you can separate the reds and whites, now they have that ability to flow through and charge can flow through it. So ionic compounds are good conductors if they're melted or if they're dissolved, right? That's why, we know that, right? So ionic compounds are good conductors if they are melted or if they are dissolved, right? And finally, as they're solids, they're actually really poor conductors of electricity because is anything moving through this crystal? No, right? They're too held strong in place when they're in their solid form, so nothing flows through this crystal. Okay? Good there. Okay with that? All right. So let's talk about covalent compounds, all right? First, covalent compounds generally have lower melting points than ionic compounds, okay? So now, some terminology, some vocab, all right? Intermolecular forces, right? Before, Chris, we talked about what? What kind of forces did we talk about at the beginning? You could look at your outline. Interionic forces, right? Are we good? First, are we good with the prefix inter, right? Between, yes, good. So interionic forces is the force between ions. Chris, what are intermolecular forces? Force between molecules, right? So, molecules. What did we say a molecule was? Anybody want to, anybody can help Chris? Go ahead, Eric. Two atoms together, but what are they held together by? Say it. Covalent bonds, right? So now we're talking about, if we're talking about intermolecular forces, we're talking about elements that are held together by covalent bonds, all right? Intermolecular forces aren't as strong as interionic forces, right? There is no conduction of electricity, even if we are dissolved or even if we are melted. Molecules, covalently bonded atoms, or covalently bonded compounds don't conduct electricity. All right? And things will dissolve not in every substance, but only in substances that are like them. You don't have to worry too much about that. We'll get into it a little. You get into it more in chemistry, but there are certain things that dissolve and certain things that don't dissolve depending on whether they're alike or not. Okay? So let's talk about why this is. Okay? Non-polar covalent bond. Do we remember what a non-polar covalent bond is? You can describe it to me. You don't have to take it like an actual definition. What is a non-polar covalent bond? Oh, good. Good. There's a nice even distribution of charge. Or those two non-metals are sharing electrons nice and evenly. Alright? Okay. Some atoms have similar attraction for electrons, so the shared pair is evenly distributed between the atoms, right? And that prevents one part of the molecule from being different than another part of the molecule. It's all very nice and evenly distributed. Okay? We don't have any side that maybe is a little more positive than the other side, or any side that's a little more negative than the other side. Right? Nice even distribution of electrons within that molecule. We call this a nonpolar covalent bond. What has to be true about the two atoms that make up a nonpolar covalent bond? True, but not all nonmetals become nonpolar covalent bonds. They have to have similar what? yes. What do we call that attraction? How do we describe that attraction for electrons? The vocab word might show up on your test. It's a big, long, multi-syllabic word. Starts with an E. Electronegativity, right? Atoms in a non-polar covalent bond have similar electronegativities, right? And that means we end up sharing those electrons nice and evenly, all right? Good there? All right, so why are interionic forces so strong? That's how we get ions, right? But like in this, right? Why is this so strong? They're attracted to each other because red has what charge? Positive, and white has negative, right? So these are real strongly attracted to each other because we have positives and negatives. Are there any positives and negatives in a non-polar covalent bond? Nice and even distribution. So, will molecules that are nonpolar attract other molecules that are nonpolar? Nope. Right? They're just kind of like, there's no attraction between them, right? Because there's no separation of charge within the molecule, they have little or no attraction for one another, right? They don't hold each other together. Okay? Does that make sense? Yeah. Are you going to write that down right now? All right. That being the case, right, let's talk about polar covalent bonds. What makes something a polar covalent bond? This is something we used last week. The electrons aren't shared evenly, right? Right? Some atoms have a greater attraction for electrons than others due to their electronegativity. Right? That means that they will form a covalent bond, they'll share, but they are not sharing evenly. We call that a polar covalent bond. All right. Good with that so far? Okay. All right. So let's take a look at these pictures. Okay. This picture you have down at the bottom of your page. Okay. You have these little blue eggs. Okay. So those blue eggs represent two atoms that are bonded together in a polar covalent bond. Okay? How do I know it's not an ionic bond? How do I know this isn't an ionic bond? What happens before we have an ionic bond? Ions, right? A transfer of electrons, and then one becomes positive and one becomes negative. There are positive and negative signs up there, but is there a separate circle for positives and a separate circle for negatives? No. That's what the first picture looked like, right on the very front page of your outline, where we had a separate positive charge and a negative charge. That's not like this. So these are not ionic bonds. The blue egg has one part negative and one part positive. That's what happens in a polar covalent bond, right? You have that sort of separation where the two sides aren't exactly the same, right? We talked about in class, like the idea of the chocolate milk that has sat on the counter for a while, right? The bottom of it is a little more chocolatey than the top of it, right? Here, the bottom of this one, come on, where's my pointer? Come back to me. Oh, that's not what I wanted. Right? Here, right? The bottom is a little more chocolatey than the top, right? Now, we refer to these as dipole forces. Polar molecules are attracted to each other because one side of them are quote-unquote negative, right? Not totally negative, like an anion, but a little bit negative. What do kind of negative things look for? Kind of positive things, right? So this egg has a kind of negative side and a kind of positive side. This egg has a kind of negative side and a kind of positive side. And so the kind of negative looks for the kind of positive. Yes, Chris?
What is that kind of positive and kind of negative?
They probably do. They didn't draw the arrow, you know. So yeah, I mean you're going to get all of that. Okay. So see this? This is water. Okay. Water is a polar compound. Okay? Red is oxygen, white is hydrogen. What are you seeing? Well, I should do this. Duh.
How much water would that actually make?
Let's finish this up here. Alright. Here's water. Red's oxygen, white's hydrogen. What are you seeing about where all the whites end up? What do the whites end up in between?
Red.
Two reds. And the reds end up between two whites, right? Similar to this, but not quite as strong. Okay? Does that make sense? And we refer to these as dipole forces because you have polar molecules being attracted to each other. Okay? Good there? All right, we'll pick it up from there tomorrow.
Wait, like if that was actually water, would that be so small you couldn't even see it?
Oh, yeah.